All right.
Cool.
Anthony, thank you.
Yeah, cool. So my name's Anthony Critelli. I'm a senior systems engineer and team lead over at Datto on our team that kind of handles all things Linux, where ironically I don't actually currently do any Kubernetes stuff in my general day-to-day, but kind of a side interest of mine. Oh, there it goes. See, it just blacked out on me again. Hold on, let me see something. This is going to drive me insane. Let me stand by.
No problem. I'll pause.
Interest of mine, and the impetus behind doing a kind of a talk focused on networking, and I've given this a few times now, is that I used to be a network engineer when I first started working in kind of IT. I was a network engineer for Harris down in Florida, actually, where I did routing and switching for the air traffic control, basically, for the FAA. And kind of stuck with networking for a few years, and eventually decided I would rather do kind of Linux and DevOps and system stuff. And so I've been doing that ever since. So the reason I kind of find networking to be a notably interesting topic is that kind of understanding how your network works is central to building any kind of robust system, and then in particular troubleshooting it later. So I find a lot of people might not pay much attention to the network when they architect something, and then next thing you know, like they have some issue, and they inevitably don't really understand how to troubleshoot it because they don't really know how the traffic is flowing, or how to identify some common pain points that you might be able to kind of avoid entirely if you spent the time to understand how everything works under the hood from a network perspective. And this is particularly true, I found, kind of in the Kubernetes ecosystem, where there's a lot of like hand waving over how over a lot of stuff, but in particular how networking works. So I've attended a talk or two where you kind of ask how some networking product in K8s works, and the answer is like, oh, you just kube control -f this manifest, and it's like, well, no, that's not how the network works, right? Like that's how you deploy some kind of network configuration on your cluster. But I mean, what protocols is something using? What do your traffic flows look like? Those are all important aspects of the architecture to understand. So that's kind of the impetus for giving this presentation and putting it together. So I kind of make some assumptions. They're not great ones, but the first assumption is that you kind of are comfortable with Kubernetes as a concept. But if you're not, I can give you kind of a drive-by explanation of the topics you'll need to know for this talk. So one of the key concepts in Kubernetes is this idea of a node, and that's a host in your Kubernetes environment that's running the Kubernetes stack. That's very roughly analogous to a hypervisor if you come from traditional virtualization backgrounds. And so you have these nodes and you put workload on them. And then when we talk about workload, we talk about pods. So pods are the smallest unit of work in Kubernetes that can be scheduled. So very often in a simple environment, this will be a single container. But if you have more complex environments, you can deploy multiple containers in the same pods. But the important thing to know is that a pod gets scheduled onto a node. And once it's on a node, it doesn't move. If you want to take a pod and put it somewhere else, you don't do that. You destroy the pod and you bring it up on another node in the cluster. And then finally, there's this concept in Kubernetes of services. And that's where you can have groups of pods that expose a network service that other pods or even external users can consume. So like kind of the idea of a Kubernetes service is very much like services that I'm sure everybody is familiar with, because I know the crowd is probably primarily development based. So those are kind of the key concepts in Kubernetes land that are important to understand for this talk. And then it sounds like a dumb question, but when I say talking about like Kubernetes networking, what exactly does that mean? What problems do you have to solve when it comes to networking in Kubernetes? And that might seem obvious if you're familiar with this, but if you take a step back, we have a couple of distinct problems we're really trying to accomplish or to solve when we talk about networking both inside and outside of a Kubernetes cluster. The first thing is that workloads, so the pods in our cluster, they might want to be able to talk to each other, right? So pod A might want to talk to pod B because it wants to consume something that pod B is hosting. Similarly, you want pods inside of your cluster to be able to talk to the services that are inside of your cluster. So if I host kind of a web service in my cluster, there might be pods that consume things from that web service, and I want them to be able to use that service construct to talk to the pods that are hosting that service. And then finally, we want external users, because none of this does much good if nobody outside of the cluster can talk to the services. So we want external users to be able to get traffic into the cluster and to be able to consume those things that our cluster is offering. And I'm going to look at each one of these kind of in turn here. And we will start with how networking works directly inside of the cluster itself. So this is just as a refresher from what I just said. There's really two problems we're solving here. We want pods to be able to talk to each other, and we want groups of pods to be able to expose services that other pods can then access. And I realize this is a lot of using the same words. So an example might be kind of good here. This is a very contrived example, but you can imagine that you have a bunch of pods that are hosting etcd, and that exposes an etcd service that is accessible over a single IP address. So any pod in the cluster can access this IP address that I have listed here of 192.168.100.1, and it can talk to etcd effectively, right? And then you might have a web service that has many other pods that make up that service, and that wants to talk to that etcd service for whatever reason, right? To get configuration, to get whatever you want out of etcd. And none of the pods care about the physical network. They don't really care about the IP addressing. They certainly can use DNS to even abstract that away further, but like they're not interested in how the traffic gets to where it needs to go. They just know they want to talk to etcd, and Kubernetes needs a way to figure that out effectively. So let's start at the lowest level and look at how pods themselves get networking configuration. So there's a defined standard called the Container Network Interface. And that basically is concerned with the way a pod itself is networked in the Kubernetes cluster. So Kubernetes takes a pretty firm stance in that every pod gets its own IP address, and a container network interface plugin in the cluster, so a piece of software running in your Kubernetes cluster, that handles allocating and deallocating the network resources as pods are created and destroyed. So network resources being IP addresses, interfaces. You might have to configure some routes to get things to flow where they need to flow. The container network interface handles that stuff. The plugin, the software that you're running to do CNI does that stuff. So when a pod's created, it makes sure it gets a unique IP address. It makes sure that other pods in the cluster can talk to that IP address, and all of that's kind of abstracted away from the operator. Now, generally, you wouldn't just deploy a CNI plugin. You deploy what's called a network plugin in Kubernetes. And as part of that network plugin, it also implements a CNI. And there are many other features that a network plugin will offer to do other network-related things inside of the cluster. And if you were to browse to that link I have there, I'll share the slides out in general afterwards. You'll see there are a lot of options. And it's, might seem like a simple problem to have a lot of options for, but there's lots of features that you can use with these different plugins, and we'll talk a little bit about some examples of features as we move forward. But let's keep focusing on how exactly the container network interface works. So pods, if you're familiar with containerization at all, pods run in their own network namespace. And if you're unfamiliar with the concept of namespacing, it's a way for Linux to isolate resources, essentially. So when you have a process, or in this case, a pod running in its own network namespace, it can only see the interfaces that are also created in that namespace. So if you spin up a pod in its own isolated network namespace and you do like an if config, you're not going to be able to see like the hosts interfaces like ETH1 or ETH0 or WLAN0 if you're on a wireless network. You're only going to be able to see those network interfaces that explicitly get put into that network namespace. So this kind of begs the question that if you have a pod or a process living in its own namespace, that doesn't really do it much good. How does it get out to the host? And this is done via this Linux kernel feature called virtual Ethernet pairs. I refer to them as VETHs. So you have an interface that exists inside of the pod namespace, and that's isolated. And then you have an interface that exists on the host in the default network namespace. I typically use the term host to refer to the default network namespace. And then what the VETH does is it bridges these two together. So you take the isolated interface running inside the pod, and you take the interface that's running in the default network namespace, and then the virtual Ethernet pair kind of tunnels that traffic between the two, and that's how the pod can get out to external network resources. So if we what I want to do is step through exactly what this looks like on a host. So I assume that everybody's comfortable at like the Linux command line. But the first thing I'm doing in that example is I'm getting a pod inside of my demo namespace called demo pod 6. And I can see, looking through the columns, it's got an IP address of 10.205.133.129. And I can see it's running on Raspberry Pi 02. There's a cluster sitting on my desk right behind my laptop here. And then if I hop over to that Raspberry Pi node and I just do a Docker PS and grep for demo, there's almost certainly a better way to do this, but this is just a quick way to do it. I can see there are currently 2 containers running that are related to the pod name of demo 6. And we're not going to care about the pause container. I linked an article somewhere in the speaker notes that explains that in more depth. But that first container there that's running Alpine, that's just sleeping for 10,000 seconds, that's the workload container. And since this is just a demo, all it's doing is sleeping. But you can see that's got a container ID of that nasty 7D, 927, et cetera, container ID. So that's our container. That's the container running inside of this pod, because there's technically 2 containers inside of the pod. So if we can take that container and enter into it and look at it and see what stuff exists in its network namespace, which we're going to do next. So the first thing I'm going to do is get the process ID of that container, because containers are just processes, and processes are put into their own namespaces. And then I'm going to use the nsenter command to jump into that namespace and execute an arbitrary command. So in this case, I'm just doing IP-brief address show, which will print out the addresses. If you're not familiar with that IP-BRA syntax, it's just shorthand for IP-brief address. And the brief presents this kind of nice tabular view. And you can see there on that ETH0 at interface 50, that has that 10.205.133.129 IP address that I mentioned earlier and we saw in the kube control output. So that's the IP of my pod. And that interface, that ETH0, only exists inside of the network namespace for this particular pod. So that gets us inside of the pod and inside of a container running in that pod. And now we want to figure out how do we get that traffic and how do we bridge that to the host. So I can use nsenter again, and I can use the ethtool command. And when you run an ethtool-s with the interface name, it'll actually tell you what the peer interface index is. So that's the peer on the other side of the virtual Ethernet tunnel. And that other side of the virtual Ethernet tunnel, that's the default network namespace, or the node, or the host, if you will. And we see on the other side of that, we've got an interface index of 50. And if you, then in that next picture there, if you do an IP link show and just grep for an interface index of 50, you can see that the host side interface is this long Calico generated interface name, and that is also in turn bridged to an interface with interface index 4. So what's going on here is I have ETH0 in my pod's namespace, and that ETH0 is bridged to interface 50 inside of the default network namespace, and that gets me onto the host. But what I do want to do next is find out about what this interface index 4 is. And if you do that real quick and just do a grep for an interface with index 4, you'll see that's just the Docker bridge. And that's about as far as I'm going to go for this particular example. But from here, you could you can get out to the host effectively, right? So now the traffic that's egressing that pod has made it to the Docker bridge, and normal routing and switching rules from Linux land kind of apply there. We can use the host routing table and get our traffic out pretty simply. So that's basically everything that goes into just getting a pod, a piece of workload in Kubernetes out to the outside world effectively. And Jeff, I'm just going to ask you to keep clicking through this until I say stop, basically. But I have here the exact same example. Go ahead and next through that. And this is just the exact same example, and it's overlaid on top of a diagram, so you can get some clarity on how this works. And I'll share these slides out, and you can just keep clicking until you can't click anymore, basically. But I kind of walk through how each piece of information is obtained to understand what the network looks like until you get out to the host effectively. Perfect, thanks. And so I mentioned, like, this is just the container network interface. This is just getting our pods to be able to talk to the outside world and vice versa. But a network plugin does more than just hand out IP addresses. So we're going to look at a couple of examples of advanced things and topologies that you can accomplish with a network plugin. Specifically, I'm looking at the Calico network plugin, because if you kind of YOLO your way through like a medium tutorial on deploying Kubernetes, they're almost certainly going to have you deploy Calico. But there are many different network plugins, all of which kind of contain their own features. But if you think about a really basic Kubernetes topology, all of your nodes might just be on the same layer 2 subnet. They might just all be plugged into a switch. That's kind of the case in my environment here. And really, in that case, all the network plugin has to do is hand out IP addresses and make sure that containers have interfaces. But there are more advanced topologies to be aware of that you might use as you kind of scale Kubernetes out. So, a common use case is advertising pod IP addresses with BGP. So you can do more layer 3 traffic control. Stretching layer 2, I have a diagram. I'll show what that looks like. And then things like Calico, for example, also let you do firewalling and security controls. So I might annotate my pods. You can have these things called annotations in Kubernetes in such a way that tells Calico to only permit traffic between, say, a pod and other pods it's authorized to talk to. This is distinct from doing service mesh stuff, which I'm not going to talk about at all. But some network plugins, if you're just looking at doing basic layer 3 traffic filtering and up to layer 4, I suppose, can do basic things like this kind of filtering right in the network plugin, which is kind of cool. So now I want to look at two very simple examples of features that of topologies you might deploy with a network plugin. And the first one is kind of that exact extra simple topology I described. In this example, you've got a whole bunch of nodes that are clearly all on one subnet, 192.168.0/24, presumably. And all of the pods, despite the fact that they're all on separate hosts, they've all got IP addresses that are in the same layer 2 domain, right? And so there's lots of considerations with a topology like this and with the network plugin you deploy. So if pod 1 running on node 1 wanted to talk to, say, pod 7 running on node 3, the first thing it's going to try to do is ARP for the IP address of that pod. And depending on how your network plugin handles things, it might intercept that ARP request and tell it where to go. Or that ARP request might actually make it out to the wire and filter its way up to node 3. And as you kind of horizontally scale in that ladder scenario, you end up with a lot of broadcast traffic on your network. So things like that are critical to understand when you're building out, if you're doing an on-prem Kubernetes cluster, when you're building things out, to understand how the traffic flows, right? Because if I was a network engineer coming from a classical networking background, I'm trying to figure out why pod 1 can't talk to pod 7, the first thing I'm going to do is traffic capture over on node 3 and look for the ARP request getting to node 3. If I don't think that, having a classical networking background, I might assume that something's wrong. But in reality, my network plugin might be just intercepting that ARP request for efficiency reasons. And so that might not be indicative of a problem. So understanding how the network plugin implements things like this is fairly important to building out any kind of robust topology. And then the next example I want to look at is stretch layer 2. So if you look at this example, you have on the left node 1 on this 192.168 network. And then on the right, there's nodes 2 and 3 on a 172 network, and there's a router in between them. So these nodes can't talk to each other directly without transiting a router. And the interesting thing about this topology is that you'll notice that all of the pods are still in the same subnet. And this is accomplished via the use of some kind of tunneling protocol. So in this case, when pod 1 wants to talk on node 1, wants to talk to, say, pod 6 on node 2, the network plugin is going to handle, transparent to the operator, is going to handle taking that traffic, putting an encapsulation around it, and sending it to node 2. And then node 2 is going to pop off that encapsulation, and then it's going to send it to the pod where it's supposed to go. And it does kind of all this for you. And this is a great example. If you've ever done anything like VXLAN, you would know immediately there are caveats to this. And they all have to do with things like MTU, which is the maximum either frame size at layer 2 or packet size at layer 3 that you can send. So if you, say, have workloads that send lots of large packets and you're not cognizant of the maximum transmissible unit on the wire, you can end up in situations where every large packet your application is sending might actually take 2 packets to get to its destination because it gets fragmented along the way. And so things like fragmentation and MTU size are very common gotchas in topologies like this that use tunneling to let workloads talk to each other. And so again, this is a great example of why it's important to kind of be aware of how networking works in the Kubernetes world. So far I've only talked about pod-to-pod communication. I kind of haven't talked about that service thing at all. And you remember at the beginning I said that if you're not familiar with Kubernetes, one of the most powerful things it offers is this idea of a service, that a single IP address can host a service, and pods don't really need to worry about who's hosting it, just that if they make a request to that IP, they'll get back an appropriate response. And so there could be one pod that's servicing that service on the back end, or there could be 1,000 pods, and the consumer doesn't care. It just knows I hit one IP address and I get back a response. So how do we do that? How do we make a single IP reachable everywhere and make sure that multiple pods can, or one pod can help service that request, multiple pods can service that request? What happens if a pod tries to access a service and those pods that host it are on a totally different node? Like, what do we do? How does that work? And this is where a thing called the kube-proxy comes in. And this is a piece of software that runs on every single node in the network. And what it effectively does is it programs IP tables, rules, and network configuration that make these service things work. And if you ever, it doesn't have to use strictly IP tables. I'll mention that on the next slide. But typically people deploy it in IP tables mode. And if you ever have the opportunity to be on a Kubernetes node and you just do an IP tables -save, which will dump the current contents of IP tables into a loadable format, and you just look at how many rules there are, it's like absolutely absurd. I think when I took this screen capture of 559 rules, give or take a few, some of those are comments, I think I was running like 3 pods on the entire cluster and maybe 2 or 3 services. And that's how many IP tables rules it takes to make kind of all of this magic happen. But I'm going to walk through an example of what this looks like and make a bit of an assumption that you're comfortable with IP table syntax, but I'll be happy to walk through as much as possible what it looks like, because this is kind of an area where it gets confusing kind of quick. So this kube-proxy thing, internally inside of the cluster, a service is exposed via that single IP address. That's called a cluster IP. And what allows any pod to hit that cluster IP is this kube-proxy. And typically, as I mentioned, it'll program IP tables rules. It also supports the use of IP virtual servers, IPVS, which is a native in-kernel load balancing feature that's baked into Linux. And it itself, the kube-proxy software itself, can also handle the proxying for you in kind of user land. But IP tables is kind of a common way to do it. So let's take an example service and walk through kind of from the top to the bottom how a pod would get to talk to that service. So in this example below, I'm dumping out the services that exist in my cluster, and there's one that we're going to look at in particular. It's the top one, and that's called HAS-service. It's Home Assistant, the home automation platform. And its cluster IP is 10.103.220.213. So if any pod in my environment tries to hit that IP, it will get a response from a pod that is hosting the HAS service that I have configured to do that. So let's look at how this works. So the first thing I want to do is just run kube-control to describe the service and look at some of the ports that are in play here. And there are 3 that we're going to look at. The first is just called port, and that's the port that the service is accessible on from inside the cluster. So this is a web service. So when another pod requests something from this HAS service, it's going to go over port 80 because it's just a simple web service. And then there's the target port. So this is where Kubernetes is going to forward traffic to inside of the container. So this is the port that the application itself is running on inside of the container. And there's something called a NodePort as well, which we'll talk more about later. And that's where the service is accessible from on the node. So if I were on the node, like logged in on a shell, and I curled localhost 31,842, I'd get back a response from one of these Home Assistant pods that are running. So those are the 3 ports we're going to look at over the course of this kind of discussion. So we will start with, go ahead, next slide. Thanks. So the first thing I'm going to do is prove to you that what I'm saying isn't a lie. And in the first example here, I'm running a kube-control exec. I'm jumping into another pod in my environment, and I'm running a curl to that IP on port 80 that I told you I'd be able to get a response from. And as you can see, I'm clearly getting a web response back. So that tells me that a random pod in my cluster can hit that cluster IP of that service and get back a response, just as I said you'd expect. And then the target port is that I mentioned that the app listens on that inside of the container. So here, if I jump inside of the pod and just run a netstat, I can see that there is an app listening on port 8123. That's the port that Home Assistant, the application itself, is listening on. And finally, that node port thing, if I'm logged into one of my random nodes and I just curl localhost at 31,842, I get back the same web request that you see I got back earlier there in the example. So all three of those ports clearly work. So let's see how exactly they work, right? So the first thing I'm going to do is jump on a host in my Kubernetes network and look at the pre-routing chain inside of the NAT table and IP tables. If you're not familiar with IP tables or really comfortable with it, it gets very confusing very quick. I linked a couple articles in the notes that go over kind of chain processing order. But kind of suffice it to say that this is where the traffic, we start caring about the traffic in this example. 1 second. So the first thing I'm going to look at here is I can see there's some rules here, and it's actually not particularly long. Like that pre-routing chain is actually pretty small. There's 3 rules there, and there's really not a lot going on. But we're talking about services, so I have a suspicion that the kube services chain is going to be relevant. And you can see that second rule down is a jump into another chain. So all traffic, that's what 0.0.0.0/0 means, all traffic will get sent to that kube services chain. So if we take a look at that kube services chain in that next kind of box screenshot there, and I grep for my cluster IP address, I can see that there are 2 rules related to that IP. So traffic that's going to that IP address. The first has to do with marking the traffic for doing source NAT later. I'm actually not going to talk about that at all for the purpose of this conversation. But the second rule in that chain, that cube-svc-unique identifier, that looks relevant because I can see a source of zeros. So any traffic going to my cluster IP is going to get bounced over to that chain. So let's take a look at that and see what stuff looks like in that chain. So if I look at that cube SVC chain, I can see this is actually just another layer of indirection. It sends me to yet another IP tables chain. I'm not 100% sure on why this is. I imagine that you could put more rules in here, but for some reason there aren't any. But if I go and I look at that chain, that cube-SEP chain, I can see there's another mark rule that I'm going to kind of hand wave over for the moment. But there's a destination NAT rule. And that's relevant to our use case here. You'll see that over on the right, it says TCP DNAT and then unsupported revision. This is kind of an unfortunate side effect of, I think, the kernel version I'm running on these hosts and the IP tables version. They conflict for some reason. But what you would expect to see here is that any traffic going to that cluster IP address is actually going to get destination NATed. So the destination address is going to get switched to the IP address of a pod that can actually service that request. So if you hit the next slide here, I have an example of what this should look like from a different VM that I'm running. And if I look at this kube SEP chain, I can see that the traffic in this case gets NATed to 172.17.0.5 on port 80. And if I look at a pod, that is clearly a pod running inside my environment. So what's happening here is when a pod wants to talk to a service, that cluster IP address, that doesn't actually exist. That cluster IP needs to get translated to an IP address of a pod that can service that request. And that's exactly what's happening here. It filters all the way down through IP tables, and you eventually get to the point where you've got a translation that takes the cluster IP and maps it to a pod that can service the request, and then everything kind of just flows normally from there. So that's kind of how services work, which sounds really kind of complex and horrifying. But once you've kind of worked through a few examples, it's actually not as terrifying as it looks, I promise, believe me. But this is all just internal cluster networking, right? Like we haven't talked about users or anybody outside of our cluster getting access to the services inside of it. And really, if you're building something like Kubernetes, you're not building it to talk to itself. You're building it to talk to external users. So let's see what that kind of looks like. You got yourself a service with pods helping it. Each pod's got an IP address, and it can talk to the world because of that whole network plugin and container network interface thing. And internally, your service is working just fine. But there's 3 main ways we let external users reach services inside of our cluster. And those are node ports, load balancers, and this thing called external name, which is DNS based, and I'm not going to talk about it all tonight, but I am going to look at the first two in turn. And there's kind of an honorable mention for ingress controller as well, but I didn't have the time to work that into this set of slides when I made them. So the simplest way of exposing a service outside of your cluster is with that node port concept. So with a node port, what it does is it opens up a random port on all of the hosts in the cluster. So if I have three nodes in the cluster, and I use a node port, all three nodes will have the same random high number port opened up for my service. And any traffic that goes to any of the nodes will get forwarded to the correct pod. And it doesn't actually matter if that pod is running locally on that node. If it's not, the node will just proxy it for you and get it where it needs to go. This is kind of a lot of overhead if you think about it, right? Like, let's say you're running a bunch of web services. Like, you're obviously not going to give out, let's say you're running 300 web services. You're probably not going to want to give out 300 random high number ports to end users. So really, you need to put like your own load balancing in front of this to make this kind of a tenable solution. But it is very simple. There's really no IP address configuration necessary here. It works right out of the box. You don't really need to do anything special to make this a thing. And honestly, a lot of load balancers now, they've got good APIs, so you could work this into your, kind of your container orchestration workflow to set things up on the load balancer side. But this is kind of a pain in the ass. So a better way to do this is going to be through the load balancer thing I talked about. But to kind of illustrate through an example what this looks like, here I've got myself a user. All of my nodes in my network have opened up port 31,842. And any node my user goes to on that port will have that traffic proxied to the service on the back end. And the service on the back end is obviously just an abstraction around pods. So if I had a pod running on node 2 that could service my request, that pod would respond right from node 2. If there were no pods on node 2 would handle proxying my request to, say, node 1 or node 3, depending on where in the cluster pods exist that can actually service that workload. So that's a very simple way of kind of accomplishing this with a decent chunk of administrative overhead. But if we look at the load balancer construct, which is on the next slide here. Oh, cool. I have more command line examples. Sorry, it's been a few weeks since I went over this. If you do kube control get services to print out a list of all your services, you can see that this service here is running on port 80. It's exposing a node port of 31,018. There's only one pod servicing this service. It's over on node Raspberry Pi 03. And go ahead to the next slide there. But I can hit that port on any node. So if I make an HTTP request to Raspberry 3, 2, or 1, I get back the same 200 OK response that I would expect. So this is just kind of proof that any node in the cluster is capable of servicing that workload. And so since the pod is running on Raspberry 3, that response will come directly from Raspberry 3. The other two, or from a pod on Raspberry 3. The other two nodes that will get clustered. So yeah, so that's kind of a node port. I think that's the last slide I had related to node. Yeah, perfect. But really, when we talk about like services, usually you're most commonly thinking about like IP addresses, right? Or DNS names, really, in most mature environments. But really, we want an IP. We want a single thing, not some high-numbered port that's hard to remember. So this is where load balancers come in. So load balancers are, to me, one of the most fascinating areas of Kubernetes because it's really where Kubernetes shows its colors and assumes you've drowned in a bucket of cloud Kool-Aid, because there's actually no reference architecture for doing a load balancer on premises. There just happens to be this project called MetalLB Fundamentals that some guy wrote, I think, while he was at Google, and we're all just hoping he maintains because it's literally the only way to do this on-prem currently. But the idea of a load balancer is that it gives an externally reachable IP address to the service, and then the load balancer is responsible for getting the traffic into the cluster. So if you're running K8s on AWS, load balancers just are glue calls to those, to like the AWS API to get you, an external load balancer, whatever AWS magic goes on. I don't work in AWS every day, but the idea is in generally that if you deployed a load balancer service in your cluster, it would talk to AWS, it would get you a public IP, and then it would worry about how to get that traffic to your cluster. But because I'm kind of talking, you've noticed my focus has been on premises, because doing an on-prem deployment lets you understand things kind of the most in depth. I'm going to look at MetalLB because that's the way to do it on-prem. So I'll talk about the fundamentals here. You configure this load balancer with pools of IP addresses, and then when your services spin up, MetalLB will hand out an IP address to that service. And it's got two key modes of operation, and they're very important to understand if you're doing anything on-prem. The first mode is called ARP mode. Second mode is called BGP mode. And so when running in ARP mode, all of the nodes that have pods for a service will respond to ARP requests for the service's external IP. But if you have any networking knowledge at all, there's a very obvious problem with this. It means that only one node can be active at a given time, because otherwise you can't do any kind of session state at all. And I don't mean layer 7 session state. I mean you can't even establish a TCP handshake, because you can't have two distinct things claiming to have the same IP address. Because otherwise, let's say if everybody's familiar with the SYN-SYN-ACK three-way handshake of TCP, my SYN might go to one pod, my SYN-ACK might go to, or my ACK might go to another pod. So like that doesn't work, right? So what this actually means is that you really have active failover scenario here. And this is like super important to understand, because if you deploy MetalLB in ARP mode and say you deploy two pods on two different nodes to host service, and you start wondering, hey, why am I only able to do 50% of the throughput or whatever that I expect? The answer is because only one pod is active at a time. The other one is sitting there waiting to take over in case there's a failure event. Now, BGP mode allows you to do true equal cost multipathing, ECMP, and that's because you can advertise the same IP address via BGP to an upstream router, and you will deterministically always have the same source traffic sent to the same destination because of the way hashing works in BGP load balancing. But you do need to be cognizant of other things like BGP topology reconvergences, which will temporarily black hole all traffic while it does a topology recomputation. So those are things that you kind of need to be aware of when running in that mode. So the first thing I'll look at here is a topology diagram of what this looks like running in ARP mode. You can see here I've got two users. They're making a request to this 192.168.0.50 IP address, and node 1 is responding to ARP requests for that IP. So all of the traffic for this service is always going to go to node 1, even though node 2 also has one of these web app pods scheduled on it and ready to take workload. Now, if node 1 were to fail for some reason, or the pod on node 1 were to fail, node 1 would stop responding to those ARPs, and node 2 would be able to take over the workload. But you're only ever able to have one active node in this environment. And that is obviously a significant drawback in some topologies, and not in others, right? This is a pretty simple, easy thing to reason about. So for some topologies, that's fine. Now, if you run in BGP mode, you can see both user requests. Now, in this case, because both nodes are advertising that address via BGP to the router says, oh, I can take user 1's flow and hash it over here to node 1, and I can take user 2's flow and hash it over here to node 2. And now you can deterministically have a user's flow go to the same correct node. And now you can do equal cost multipathing. So if I added 5 more nodes here and they all advertise that same address, the router would be able to load balance across all 5 advertisements it received, and subsequently all 5 nodes with that IP. So that's kind of neat. And that's kind of potentially a better way to kind of do this scalably. So I only have a few more things I wanted to mention because I know it's a lot of talking, and I know this is probably very like sys and network heavy. So hopefully that's okay with some of you. But the kind of the thing I want to really give an example of, and I have an example here, and I have the chat window open. So if you can figure out what my issue is without skipping ahead, I'll give you a second. But I really think networking is very important to understand. This is especially true in like the cloud native ecosystems, whatever that means. Because a lot of times this stuff is like totally abstracted away from you. People will just kind of hand wave over network configuration and like it's fine until it breaks. And then like if you literally don't even know how a pod gets an IP address, you're not going to know how to begin troubleshooting where in the network something might be broken, right? like as a kind of a former network guy, one of my first go-to things when troubleshooting things on networks is TCP dump. And like, if you literally don't even know where the traffic should be going, you're not going to know where to begin TCP dumping to, to troubleshoot. But like, it's actually not that hard. And I know it seems like this is probably a lot of IP tables and systems heavy focused content, so it might seem really complex. But kind of the reality here is that it's not actually that bad, because network fundamentals are just network fundamentals, right? These are just like standard network protocols, standard things like IP tables that have been around forever and are well understood, and you can kind of work with. So, a really great example in my environment here, when I was first standing up my local Kubernetes environment, I had configured Metal Load Balancer to hand out IP addresses on a wireless subnet. And I noticed that every 5 minutes, I would suddenly be unable to reach one of my services. But if I started packet capturing to troubleshoot this, the problem would immediately go away. And so I'll like give it a second and like try to put some filler in. If anybody knows what my problem might have been, feel free to drop it in the group chat. But like, this was like a very frustrating thing to troubleshoot, because I use Meraki firewall gear, which is not really conducive to doing like lots of deep dive into like what's going on your network. So I had to like kind of troubleshoot blind for a little while. And it made things like doing ARP table clears and stuff very hard. But go ahead and go to the next slide there, Jeff. Thanks. And so the issue actually was pretty interesting. So the symptom is pretty obvious if you have any network background. Every time, if you're losing connectivity every 5 minutes, it's almost definitely related to ARP layer 2 protocol that resolves an IP address to a MAC address. And so for some reason, I noticed that every 5 minutes, Metal Load Balancer would stop responding to ARP requests for the service's IP. And so, the traffic effectively got black-holed because the router didn't know where to send the traffic. But why does the problem go away when I tried packet capturing? And if you know how TCP dump works, it puts your interface into promiscuous mode. So that an interface that's running in promiscuous mode is going to receive all packets sent to it and pass them up to the higher levels of the stack, instead of discarding them at lower levels of the stack. So effectively, when you're in promiscuous mode, even if you get some traffic on your network interface that's for an IP address that you don't own, that's not like physically on your network configuration, it'll still pass that traffic up. And that's the case with MetalLB, right? It's trying to respond to ARP requests for IP addresses that aren't actually configured on the host. So by turning on TCP dump, it made that go away because it puts the interface into promiscuous mode, and then the traffic filters its way up. And the eventual, like the end-all solution here was just to set the network interface cards on these Raspberry Pis to be in promiscuous mode all the time, so that they would always filter that traffic where it needs to go. I don't know if that's a Raspberry Piism or if that's a Linux kernelism. I never dug into it much further than that. But that's like kind of a really good, genuine example of a problem I ran into. Similarly, if you deploy Calico as your network plugin, it really advocates for a very simple network topology without encapsulation. So doing that whole, like, all of your pods are on the same layer 2 subnet and there's really nothing to think about, except if you deploy it using their default deployment method, it actually gives you encapsulation. And if you didn't know that, when I was doing packet captures, like, I didn't know that until I started digging into it. It made troubleshooting kind of obtuse because I was thinking that it wasn't doing something that it actually was doing. Same thing with the fact that it kind of randomly picks an interface on your machine to use for that traffic. So in my case, I have my nodes in my cluster hooked up to a physical switch, and then they're on the wireless network for internet access, but they're using the wireless network for the internode traffic instead of the backend switch, which is faster. So if you don't really know how the networking stuff is deployed, it's very hard to troubleshoot and understand like where your traffic is supposed to be going. So the last thing I throw in here is just some useful resources that I had while working through this. Like I said, I'll share the slide deck. I've also got presenter notes galore in there. But these were good articles that helped me understand how some of this works and dig deeper into the fundamental concepts of how all that went. So I'll make those available as well. And that's literally all I've got. So Jeff, thank you for sharing and getting past whatever the hell was going on with Zoom. That was super frustrating. I appreciate your patience there. And hopefully, like I said, I know that this is probably more of a software engineering oriented crowd, but hopefully you found kind of the deep dive into the systems world interesting. So thanks. And if you have any questions, certainly happy to take those as well.
Yeah, thank you. I'm going to set up my own little Raspberry Pi cluster at some point with MetalLB too. So
Yeah, let me know how it goes. It's actually not that hard to do. I think I did most of this in an afternoon. So.
oh, perfect. What are you running for Kubernetes? Are you running K3s?
No, I'm actually using kube-ADM because I wanted to figure out how to deploy kube-ADM. But a friend of mine, a colleague, he recommended there's I think it's OpenSUSE has a project now, which is just like Kubernetes in an image. So like I have all this Ansibleized, so my entire cluster comes up via Ansible. And he was like, he pointed me at this thing that you can basically just write the image out to a disk and you've got yourself a Kubernetes cluster. So I might check that out at some point too. But yeah, in my case, I'm just using kube-ADM. So
that's cool.
So one question about your Raspberry Pi example there. What are the performance implications of running everything in promiscuous mode all the time?
I'm actually not sure. That's a good question. I don't actually know. I'm not sure how. I've never really looked into how far up the stack those packets get processed before they're discarded. Like I think the biggest concern would be a copy from kernel space to user space for each packet, which I have to imagine is going on because I can't imagine MetalLB runs in anything in kernel space. But yeah, I guess I'm not sure. I would be curious. You mentioned it. Sorry, bad answer. Cool. All right. I guess that's.
Okay. I've got a quick question.
Sure.
Why is MetalLB necessary when I think Kubernetes, I mean, just the virtue of a service provides some degree of load balancing across the pods?
Yeah, good question. So the MetalLB side, the entire load balancer aspects of service comes from external traffic into the cluster. So the service inside of Kubernetes exposes itself on something called the cluster IP, and that IP is only accessible from within the cluster. So the entire idea of services, of load balanced services, the load balancer service type is only for getting external traffic into the cluster.
Okay.
Yeah, if you deploy a service in Kubernetes by default, it gets a cluster IP, but you can only get to that inside of the cluster.
Gotcha.
Yeah.
Thank you.
Sure.
You mentioned the ARP every 5 minutes. Why is it 5 minutes?
It's just like the default timer on my upstream networking gear, which happens to not be configurable. So typically when you, I mean, you can check it on your laptop too with ARP-A, but you know, when you do an ARP resolution, it starts a timer so that the cache entry will eventually time out. So you're not ARPing for every single packet, right? And generally, as long as you keep receiving traffic to and from that host, the timer will keep refreshing and things will be happy. But that's done and is particularly useful because let's say an IP address actually moves to a different device. Now you actually do want that to time out after a while so that it can pick up the new MAC address. There's also this thing called gratuitous ARP that things like MetalLB does, which is to send out like when a new service comes up, it'll send out an ARP broadcast to say, hey, this IP is over here. That way you don't actually have to wait for that initial back and forth. Same thing when like if you pop up 3 slides from where you are there real quick to that ARP mode, the other direction, sorry. One more.
There we go.
So you do things called gratuitous ARPs in scenarios like this where let's say node 1 fails. Suddenly it's not going to be able to respond to ARPs for that IP address. So if that router has a cache entry on it, it's going to have to wait for 5 minutes until it times out and sends another ARP request. So when that failure happens, what would actually happen is node 2 would send out what's called a gratuitous ARP that says, hey, this IP is over here now. And the router would refresh its cache and now would be able to forward the traffic along correctly. So cool. Any other questions?
Oh,
Cool.
Thank you for the presentation.
Sure,
Thank
yeah.
you very much. That was really interesting.